This is the presentation for the paper Safe Reinforcement Learning for Urban Driving using Invariably Safe Braking Sets. A joint work from Xinjiang Chang, Matthias Althoff, and me, Hanna Krasowski. Urban driving is a very complex task. The driver has to decide if he or she wants to turn left or right at the next intersection. There are a lot of other traffic participants and traffic rules that have to be regarded. So if we want to automate this task, we want to have a rich representation which can represent this task well. So we could use reinforcement learning for that. But the problem with reinforcement learning is that you often don't know much about how this policy would behave in an unseen situation. So in this work, we extend the classical reinforcement learning approach to provably safe reinforcement learning, such that we can actually guarantee safety specifications for these urban driving situations. And we want to do this efficiently because there are a lot of decisions to make in an urban scenario, and also effectively because we actually want to go where we plan to go and not somewhere else. So for that, we designed, our contributions are that we designed a discrete high-level action space to efficiently represent all these actions. We introduce a safety layer that verifies safety with respect to the lanes and also with driving across intersections. And finally, we evaluate our approach on real-world traffic data of 3 different intersections. So here, that's the overview of the provably safe reinforcement learning. On the outer part, we have the reinforcement learning part. And then this orange safety layer, the inner part, is the extension to provably safe reinforcement learning. So as usual, our agent observes the environment through the state, selects an action, and then the reward is used to indicate how well this action was. Then in our case, we have in between this safety layer, which observes the environment with its current states of the obstacles, and it also gets the road network. And then in the safety layer, we verify which of our actions are currently safe. So for that, we use the concept of invariably safe braking sets in conflict zones. And in case that we cannot verify any of our actions as safe, we also have a fail-safe planner such that we can always select an action. And then what we end up with is an action mask that indicates which actions are safe and which not. And then this is added to the agent's policy network in a dropout layer way such that the agent can only select from the safe actions. So first, I will introduce you the reinforcement learning parts, and then I will go into detail of the verification parts. So we have here in 64-dimensional discrete action space, where the regular actions are constructed in a combinatorial way. So we have actions that indicate, or one dimension that indicates how this agent behaves with respect to lane or lane changing. Then one is how the agent behaves at the next intersection. Well, does it turn left or right or stay driving straight ahead? And then along these different reference paths that are basically identifiable from the first 2 actions, the agent can choose between different desired driving accelerations. And finally, we also have the fail-safe action as additional action in our action space. So how does the agent observe the environment? It gets 26 ego vehicle related, goal related, surrounding traffic participant related, and road network related states that are specified as for the tool common road RL. And then on top of that, we also inform the agent about the next intersection. And here, 2 of these 14 intersection related states are between the ego vehicle and the intersection. So there are these as near ego and as far ego here in this figure, which tells the agent how far, or what's the farer bound of the next intersection and what's the nearer bound. And then we also can observe up to 6 vehicles that are currently driving towards the intersection. And for each of these vehicles, we observe the distance to the intersection and also its velocity. Finally, we also need the reward. where we have terminal rewards when the goal is reached, the episode or the scenario time ends, and when a collision happens. And then if only the fail-safe action is possible, then we also give a penalty, which we call our mask. And to inform the agent better where the goal is, we have also this goal guiding reward, which helps the agent which is positive in case the agent got closer to the goal since the last training step or time step. So now let's jump into the safety verification. So here's an overview. For each time step, we first check if we actually have to do a new verification, because on some conditions we don't. So we only verify if the planning horizon was reached, if the lane changed finished, or if the road network we observed changed. And in the other cases, we just continue along the previously planned trajectory. If we need to re-verify, we verify in 2 dimensions, the lane safety and the intersection safety, which I will explain in detail right afterwards. And only if an action is in both or safe with respect to both verification processes, it's added to this safe action space. And now in case if the safe action space is empty, the agent can only select the previously calculated fail-safe action. And if it's not empty, the agent is allowed to select from any of these actions in the safe action space, and then we execute the action. So here's how the lane safety verification works. We have this invariably safe braking sets for the different lanes here. And then what we do is we iterate through all actions. Here we already, for efficiency reasons, exclude the actions that are not meaningful, that would, for example, lead off the road. And then depending on the action, we either only check the safety with respect to the vehicle in the front. So here, if we don't change our lane, we only need to be in this invariably safe braking set with respect to the leading vehicle. So we check that our planned trajectory is fully included in the safe set. And in case we want to do a lane change, we want to be safe to the vehicle which is in front of us in our current lane, and to all of the vehicles in the target lane where we want to change to. So the second dimension is intersection safety. Here we want to verify that an agent can cross the intersection safely. So again, we iterate through all actions in our discrete action space, and for each action we construct these conflict zones or these collision objects by checking for all the obstacles what are parts of the road network that can be mutually accessed by the ego vehicle and by this other vehicle. And in case there are these, then we check when the other vehicle can, what's the first possible time when the other vehicle can reach this, and then we basically block this part for the ego vehicle from then on. And then what we check in the end is if our plan is is not intersecting with these collision object, which reflects how the other vehicles could block or use the intersection before the ego vehicle. So now we want to see how our approach really performs in an experimental setting. So we use recorded data from urban scenarios of 3 German intersections from the INDI dataset. Our learning algorithm is proximal policy optimization. We train for 500 training steps and update every 2000 steps approximately our policy network. Our network is a feed-forward MLP with 2 hidden layers of 512 and 256 neurons. And we train 2 agents, a safe agent, which has our safety verification, and a baseline agent, which only has one additional feature, that it cannot select not meaningful actions that would lead off the road, because otherwise it would be much harder for the baseline agent to learn. So here you see the results for two of these three intersection examples during training. You directly see that the baseline agent performs much better than the safe agent, and the goal reaching rate is constantly lower, and but still both agents converge during training. And they don't overfit, so that we also see, because like here you can see the evaluation on the training and the test data set. So these numbers are still very similar, which indicates that we don't have overfitting. And you also see that we actually can also show in this experiments what we proved before, that we really achieve absolute safety. So the safe agent does never collide. And but the goal reaching rate is much lower, contrast to the baseline agent. But now if we look at what happens if we individually use these verification components, we see that this safety with respect to lanes even improves the goal reaching rate in contrast to the baseline. But obviously only the intersection safety and also only the lane safety will not ensure absolute safety, and we still have collisions here. So how do our results look quantitatively? So on the left side, you see the bandplots example with the safe and the unsafe agent. Both perform very similarly and reach the goal. On the right side, we have the Heckstraße example, and here you see that the unsafe agent directly collides. And the safe agent waits until the vehicle in front passes the intersection and then reaches the goal. So in this case, the safe agent even performs better than the unsafe one. So in conclusion, we achieved a provably safe reinforcement learning approach where the ego vehicle does not cause collisions. We evaluated it on up to 4 legged intersections with real traffic data, but still see that the baseline agent performs much better with respect to the goal reaching rate. So in the future, we definitely want to improve this conservativeness of the safe agent. And one way to do this would be to include more traffic rules, or because, for example, now we always wait in case some other vehicle could pass the intersection, but that's not realistic because, it's a very conservative, because in reality you would have traffic rules, and there would be also cases in which the ego vessel is allowed to go first and the other traffic participants would need to wait. So if you have any questions, feel free to contact me.